Today we begin with an informal introduction to finite automata. I'll offer some brief remarks about their uses and then move to an extended example of an automaton that describes how a game of tennis is scored. The finite automaton is a mathematical model, but fortunately it is a model that should be quite familiar. You can think of it either as a graph or as a table. The finite automaton is simple because it stores only a finite amount of information. That can be bad, because in many applications there is no limit on the amount of information we need to remember about what has happened in the past. When that is the case, the finite automaton is not a useful model. But the finiteness of memory is great when the model can be used, because we can do a number of things with finite automata that we cannot do with programs in general. For example, given a program, you cannot really tell anything about it, what it does, or whether there is a shorter program that does the same thing. However, you can tell whether two automata do the same thing, or whether there is a smaller automaton that does the same as a given automaton. You can also tell whether an automaton does anything at all. That ability lets us tell, for example, whether there are input sequences that cause an automaton to get to an error state, which in turn lets us check whether protocols or other simple systems have flaws. A finite automaton is built around a finite collection of states. Each state has a name, and that name represents what is remembered about its history. States change in response to inputs. Inputs are either characters if we're doing something like processing text, or events if we are modeling something like a communication protocol. The rules that give the new state for each current state an input are called the transitions. The finite automaton is useful in a number of computing applications. We mentioned the design and verification of communication protocols and digital circuits, and together with the related formalism called regular expressions, they are important in text searching algorithms. They are essential for the portion of a compiler that breaks the input into tokens, identifiers, keywords like if, and so on. You find automata and regular expressions in many other applications as well, typically where simple language is needed to describe patterns that are sequences of symbols or events of some sort. To see the power and also the limitations of a finite automaton, we shall take up an example, scoring a game of tennis. If you don't play tennis, it's almost like ping pong, except you are really tiny and you stand on the table. Depending on which page comes first in response to your search query, you'll find it was invented in the 12th century or in 1879 by people who evidently had too much time on their hands. The scoring system is arcane, with matches consisting of sets, which consists of games. Games consist of points where one player or the other wins by causing the other player to hit the ball off court or into the net. We'll talk about scoring a game. One player is server throughout the game. To win the game, you must have at least 4 points, but you also must win by at least 2 points. The states we are going to use for the scoring automaton represent the numbers of points won by each player, and they have strange names, which we'll see as we go. The inputs are events in which one player wins a point, S for the server wins, and O for the opponent wins. It is common to represent a finite automaton by a graph, with nodes for states and arrows labeled by the input for transitions. Here's the first state of the automaton that scores tennis games. The name of the state is love. You may ask, what's love got to do with it? But that's what 0 is called in tennis. The state love represents the history in which nothing has happened, and we indicate that history begins with this state by an arrow labeled start. The first point will be won by one of the two players, so there are 2 transitions out of love, one labeled S, the other O. You might think the names of the states would be 1-0 and 0-1, because the server's score always goes first. But they're not. In tennis, there is the fiction that you score 15 for winning a point, and 0 isn't 0, it's love. The next point can lead to 3 states, 2 where one player has won both points, and 1 where they're tied at 1 each. Here are the states with their names. There is something interesting about the 15-all state. It has forgotten how we got there. We know the sequence of inputs was either SO or OS, but we don't know which. It doesn't matter, of course. That's a good thing about finite automata. They only remember what must be remembered. In state 15 all, the question of who won the first of the 2 points can't have any effect on the outcome. After another point, there are 4 new states the game could be in. They have the expected names, except people are too lazy to say 45, so they just say 40. Now let's look at the transitions from the state 40 love. The server is well ahead and can win on the next point. If the server wins, we'll go to a state indicating that win. The game is over and the automaton has no further moves. We indicate this output of the automaton by calling the state a final state, and we indicate it as final by a double circle. There is another state reachable from the state love 40 if the next input indicates the opponent won the 4th point. There are 3 other new states as well, called 40-15, 30 all, and 15-40. Each indicates that 4 points have been played, with 3, 2, or 1 of these points won by the server. From the 40-15 state, if the server wins the point, we go to the server 1 state. But if the opponent wins the point, we go to a new state called 40-30. A similar thing happens from 15-40, and from 30 all, we can go to either the 40-30 or the 30-40 state. Now let's look at the state 40-30. If the server wins the next point, they've won the game. But if the opponent wins, then the game is tied. The name for this state is deuce. The deuce state is quite interesting. It remembers that the game is tied, but it remembers neither the sequence of wins and losses of points, nor even how many points have been played. And the 30-40 state is handled similarly. Next, consider what happens in deuce. You have to win by 2 points, so it is impossible for either player to win immediately. If the server wins the next point, they are ahead by 1 point, although we don't know how many points in total have been played. The strange name for this state is add-in, or advantage in. In refers to the server. Symmetrically, if the opponent wins in state deuce, we go to state add-out. The out refers to the opponent. Then in state add-in, if the server wins the next point, they win the game. But if the opponent wins, you're back to deuce. Likewise, from add-out, a server win puts you back in deuce, but an opponent win gives the opponent the game. We can now look at the entire transition diagram for the finite automaton. While most of it just allows flow away from the start state, the loops involving deuce, add in, and add out, that is, these, they allow for cycles and for an infinite number of possible strings of S's and O's to lead to one of the final states. The job of an automaton is to process strings of input symbols, or input strings. We always begin at the start state and we read each input symbol in order. For each input symbol, we follow the transition from the state we are in to discover what the new state is. We accept the string if we wind up in a final state after processing the entire input. Here is an example. Here is our input string. It represents a game in which the server and opponent alternate winning points until the very end, when the server wins 2 in a row. We'll mark the current state by the star, and initially the current state is the start state. That's where all finite automata start out. The arrow indicates which input we are about to process. So here we are about to process the first event where the server wins the first point. We're going to follow the transition out of the state love, labeled S. Here we've made the first transition. The next input is O, and we're in state 15 love. The transition from that state on O is to state 15 all. In state 15 all, we see another S on the input, so we go to state 30-15. And O takes us to state 30 all. Then on S, we go to state 40-30. From there, we go on O to deuce. And from deuce on S to add in. From there on O back to deuce. And another cycle on S and O between add in and deuce. Now come the first of the 2 S's. This S takes us to add in again, but the second S takes us to the server win state. Good going, server. Now let's get a bit more formal. The job of a finite automaton is to process strings of inputs and accept or reject them. It accepts the string if it leads from the start state to a final state. Accepting state is a synonym for final state. A language is simply a set of strings in the formalism used for automata. The language accepted by an automaton A is denoted L of A. In our tennis example, we called the two states where one of the players wins the final states. In that case, the language of the finite automaton is the set of strings of S's and O's that end the game, no matter who wins. We could change the set of final states, say by making only the server win state be final. Then the automaton would have a different language, the set of strings of S's and O's that lead to a win by the server. Or we could make only opponent wins be final and have the language of ways the opponents can win.